Okay, so next up is Jeremy. I saw you have a report for the NCO work, and you have the floor.
Yeah, hi. Apologies. It's just after 5 o'clock in the morning here, so I'm effectively jet lagged to a certain degree. I have some updates or questions about the some of the remote lab stuff, but I'll leave those until the end. Um, I have. Let me see if I can. I can't share my screen, but
Let
what I've
me,
tried to.
yeah, let me fix that. Sorry, I didn't set it for multiple people, but I will right now.
Yeah, okay.
Okay, please go ahead and try again.
Please go ahead and try it. Here we go. Uh, Share this. Can you see a document?
Yes, perfectly.
Um, so what I'm trying to do is bring myself up to speed on PLLs in general and specifically discrete time PLLs. I've seen some continuous time PLLs in use before, and so I've just for my own benefit have written up some of the theory behind them and also developed, the sort of typical type 2 second order loop, closed loop transfer function equation. And, brought this is all kind of standard stuff cribbed from textbooks. And, for those types of PLLs, one gets these kind of parameters that are relate to the natural frequency and the damping of a control loop, continuous time control loop. I've clarified some of the terminology around ranges, hold-in ranges, pull-in ranges, and lock-in ranges, because I've been assigned the task of looking at stability of the Costas loop in general. So I thought it was a good idea to have those well defined, and this, as part of my ongoing work, this is slightly not in the main line of and not in the critical path of what you guys are doing, I don't suppose. So I'm reading the Gardner book on phase lock techniques, and also Matthew was very kind enough to share a document that he used to develop some of the mathematics from this Gardner textbook. And so clearly there are significant differences between implementing a PLL in continuous time versus discrete time. And so here, what's on the page now, as you can see now, is our implementation of a Costas loop in discrete time. What follows is a development of the theory, including these integrators with dump and hold aspects, and I don't fully understand what these are yet, and I'm desperately reading through the textbook to get a handle on how to interpret those. So what follows on the next couple of pages is taken from the book, as you can see the reference there, and also what Matthew has. So I'm assuming what I've got here in front of me in terms of the mathematics is what's actually been implemented in the HDL itself. But I haven't yet gone through with a fine-tooth comb and verified for my own satisfaction that this is indeed what's been implemented. And so we get to the end here where the transfer function that's in discrete time. I believe this is the open loop transfer function. So what follows and what I think we have to do is something called a jury's test, which is the equivalent of a Root-Hurwitz test for stability, which is the equivalent in the continuous time domain. So this is all a bit of a work in progress. and to be honest, I need to do much more reading and much more thinking in order to come up with some, well, to address some of the points that I addressed in going through the document. So I don't know if anyone else is out there at the moment who's got lots of experience with digital signal processing and digital PLLs specifically. I believe Matthew can shed some light on some of these questions that I've got here. So in principle, I should be able to take this. Well, yeah, okay. So let's just clarify a little bit more. With the I'm thinking about using Python to be able to draw a root locus plot of the transfer function that we believe has been implemented in the HDL, and I've got some experimental code that hopefully will do that for varying the gain parameters and showing us where we've got poles and zeros and how they move about the complex plane. And that should give us some ideas of stability and so on. I haven't gone quite as far as thinking about being able to derive the lock-in and hold-in ranges for these things. I think this is what I'm supposed to be doing, but rather than simulating. Matthew, when I've talked to Matthew, he said his intention was to look at this from a more theoretical point of view and systems point of view, rather than actually implement something in simulation, which seems reasonable to me. Now that the repository has been split out in the way it's been split out, I think it may or may not make testing easier for these individual components, because, well, there'll be some question as to where the testing, at what level the testing is done, and how inputs and outputs are generated for the individual, well, stimuli, basically. It may turn out that there has to be re-implementation of, for example, an MSK modulated waveform in the testing layer, rather than coming from HDL that's already been written. And that's a question moving forward, I think, more than anything else. So if anyone thinks Jury's test is the way to go, and that I should be able to determine it from that polynomial that I've pointed out in the document, then that would be a great help. It'd also be a great help to me to understand some of the existing mathematics and how it's been implemented in the HDL. I mean, just a walkthrough would be really useful, I think, just pointing at the equations in the document and saying this is part of the HDL, and this is how the HDL is intended to work, and that kind of thing. So I don't know whether I'm doing the right things here. It's hard graft, because my control theory and my signal processing stuff I haven't done much in several years now, so it's all a bit of a steep learning curve for me. Yeah, that's about it for the update. Would you like me to just make a mention about some of the remote lab things that I was playing with? Or
Oh, yes, that would be wonderful. Please go ahead.
so it turns out that there's a web interface for the spectrum analyzer, and I set up WireGuard, and I can see the web interface, but it's basically unusable. It may be because the piece of glass connecting up me to where you guys are and where the remote lab is very, very long, and it's experiencing timeouts that is not expecting. The other thing I can do is run the vendor software, but I'm being a bit of a Linux evangelist. I don't have a Windows machine handy to do that. I understand there That's a way I can do it. Okay, so I've talked myself into my own answer. That's there must be a Windows machine around somewhere that I can log into via VNC or remote desktop protocol and use the native software to control the spectrum analyzer with. So even though it was very nicely pointed out and that there is network connected, sorry, a web-based interface to the spectrum analyzer, I was unable to use that particularly well. And I had to play around with the standard analog devices scripts repository and just get it to try and sweep its local oscillator and just get comfortable with the Pluto. I don't have one locally here to play with. I don't think it's connected up to the spectrum analyzer at the moment. I believe it's got an attenuator on the transmit output. I don't know if it's the case for the Pluto, but certainly for the Lime SCR, there's an internal loopback feature to connect TX and RX together. I suspect there's the same thing on the Pluto. So maybe it's not necessary even just the only reason I would want it is just for playing around for satisfaction that I can actually use things in the remote lab and watch what's happening. But I gather there's contention for the Pluto at the moment, so I'm not too worried about that. So I think I've mentioned this, but I have made a build of the top level Pluto MSK repository. And I'm not sure if the top level build in that repository, whether that includes the this repacking of the firmware that you're describing in part of that process. So I don't know if it's already implemented in the top level make file. I can't really add any sort of sensible comments other than on top of that. I'm just a naive user building piece of software that's uses Git modules to just manage its dependencies. So that's all for me. I'm sorry about that if that's any of that makes sense or not. It's pretty early in the morning here, but yeah, I've got my main questions and queries across.
Okay. Yeah, I think Paul can probably address some of the remote lab things. But what I can answer is that but you're doing everything totally right and keep at it. And yeah, no, a lot of us are just a few steps ahead of you in terms of knowing how to deal with all this amazing complicated stuff. So please don't ever feel bad about asking questions. Now, from my understanding, that when you clone the Pluto MSK repo and you run make, that no, the Pluto firmware is not yet automatically made. So there's still some manual steps that need to be done in order to take your bit file and your XSA that you created from this make in the MSK, Pluto MSK repository, and then you still have to fiddle with it. The goal is to make that all one process. That would be a good goal. So we're not quite there yet. So if you look on the Opulent Voice channel, you can see, and also in some of the documents, the Markdown document for working with FPGAs and for integrating IP with the HDL reference design. So there is some clunky steps still, but if you've built the MSK, a Pluto MSK repository, cloned it and built it, then what you've done is taken the reference design from Analog Devices and you've integrated custom IP into that for the MSK thing, which is pretty awesome. If you didn't see any errors, wow, that is really great news. So that's huge. And so I'll turn it over to Paul then to answer. Oh, go ahead. Sorry.
Yeah, just a remark. Right now, the Pluto SDR firmware with the open bitstream is completely automatic, right?
I don't think the firmware is automatic. Like I still had to pad.
Yeah.
Where would that
Uh,
be when you clone the Pluto
yeah,
MSK directory?
yeah,
It's
yeah. You just have to clone the Pluto MSK,
okay.
then go to firmware, and then make.
Oh, okay. Is that new,
That,
or has that
that
been the?
this is from this afternoon.
Oh, for okay. All right. So yes. All right. So Jeremy, ignore what I just said because I was still
Okay.
having to do it. So it sounds like Evereast
Yeah.
has made some big steps forward. Thank you, Evereast. That's good news. So yeah, firmware directory in that repo. That's fantastic.
Yeah.
All right, late breaking news. Big steps forward. So and then oh okay, sorry. So I'm going to turn it over to Paul. I know that we've seen evidence of operating the remote lab in the lab on the spectrum analyzer. So that was evidence that this method of accessing it has worked. So Paul, yep.
Yeah, of all things, my mouse has started acting up. Luckily, I have a backup. I'm disappointed to find out that the web interface is not working for you. That's a drag. One of the disadvantages of me being local here to the remote lab is that I only see how it works on fast connections. If you have any more details about that, it might be useful. Maybe I can do something about it. Maybe not.
Okay, I'll see if we can get some sensible information out of it. Quite often it sits at the um, Rigol banner screen, and sometimes, and when if I can get a display up, sometimes clicking on buttons, they're not responsive, and I get text popping up in the bottom left corner of the window saying connected, connected. That it doesn't. Sometimes I've managed to encourage it into giving me, like, for example, for setting a span and setting a center frequency and so on. It's come up with the little numerical input display, but it seems like there's something timing out or something not quite happening right there. Um, a solution, as I said, might be to, if there is a VM, and I believe there is a VM, a Windows VM that has access in the remote lab, I should probably just try to log on to the Windows machine and use the native Windows software to try and to access the spectrum analyzer. I guess that will be a solution. Does that sound reasonable?
It sounds reasonable, but I can't confirm from experience that it actually works. We have an actual physical machine for Windows and for some plug-in cards that we have for video, and we also have a VM. I can set you up with access to both if you want to experiment with it. I know we have the Wriggle software installed on at least one of those, but I haven't given it much of a workout. Um, that may be an alternative. It would certainly have different problems.
Yeah, let's try it. Definitely worth a shot.
Sounds good.
Awesome. And then I think the first set of questions related to how to exercise or how to do experiments with the NCO, like now that it's its own repository. And hopefully that should make it easier to work with. And then so what I think might help is to think of this as like, okay, here's this NCO that's now a standalone numerically controlled oscillator. Now it needs a test bench. So you would be writing a test bench that would then go into that repository. And so the test bench is you know, it won't hurt anything. And that would allow you to set up experiments with it. So that's kind of how I would approach it, is to kind of go ahead, treat it as a standalone repository. You'd have test bench, you'd have stimulus files, you'd have, here's what we should be getting, and you'd be able to set up experiments in Python or however you wish. Um, but the actual code, the implementation, I don't think that would hurt anything. That would be my sort of guess. Yeah, and the approach sounds good. And yes, a walkthrough of like how this particular implementation works would be good. What I think I could probably help with or encourage or dive in on would be very thorough commenting of the code. That's really that if you know, being faced with similar situations all the time, that's really the only thing that helps me, is to just work through the code and comment every line. And just, even if it's very simplistic, then that's the thing that kind of helps me, and that would kind of reveal the guts of what's going on with the NCO. So that
Oh,
would
okay.
be
So
like where I would start.
okay, so it's not so much about the NCO in particular. I think it's so the piece of work that's labeled up in the Trello board is to investigate the Costas loop. Now, I believe that's now been abstracted away into the sub-repository that's MSK demodulator.
Right.
Um,
Yeah, you're right. Thank you for the correction. That's true. So yeah,
so
it's
and the issue with that is that one would have to generate true MSK signals
mhm.
from somewhere. So that would come from that would be part of the test bench, as it were. So that might be, and we've agreed that that might be a good exercise in and of itself, to generate MSK from Python, and use CocoaDB to exercise the demodulator in that kind of way. And that's a non-trivial bit of work, I think. And the other top level question around that is that I think Matthews indicated that the piece of work that he was the sort of the Trello entry is actually less about simulating it and more about getting a hold on it from a systems perspective. And so my questions are really more about should I be making root locus diagrams and Nyquist plots of what we've got here from the theory and what we think is being implemented, and should I be applying these tests, the jury test, for example, given our theoretical transfer function. So I don't know if that's
Yeah, I
more interesting
was
or less interesting. So and whether I've got the message right here.
No, I think you do. That's a generally good approach. As for like specifically, is this jury's test the best thing to do? If it pops up in the literature, then the right thing to do is to bring the question up to essentially a review board, to have a quick design review over this, and I'll help all that I can to kind of spread the word. But yeah, I mean, getting a good handle on theoretically, what does this stuff look like? What are the different tools that you need to use in order to exercise it? We do have a decent model in Simulink for creating MSK signals that are kind of
Ah,
random bit streams, and that, so we do have a start on that, to like, okay, so here's a stimulus file and here's the expected response. So it's, you're not starting from nowhere.
so
It still
I think
needs
I've
some work in order to get it to be useful for you. You know, but things like that are the things that are probably going to help the most, to give you like, okay, here's a file. This stands for the expected MSK signal, and here is the expected response. So if that could help in any way, then we've got a good head start on that.
yeah, I think I've seen it's in the sim directory of the Pluto MSKs. That's correct.
Oh yeah, I think so. I think that might be directly from Matthew. He so yes, there we can achieve this, and it's not, you don't have to start from scratch unless you want to, you know. But you don't have to. That there are some existing artifacts for helping, you know, generate the, here's the signal, here's what you should be getting, that sort of deal.
That's a useful reminder. Thank you. I think you've already told me that, but yeah, thank you.
No,
The
we'll keep
DRAM
yeah,
DRAM has been refreshed. Yeah, thank you.
I have only empathy. In between coffee and Google Calendar, we managed to to get through things. So yeah, your general approach is really good. It sounds like it's a theoretical or systems approach. Let's see what we got here. Let's really like drill down and like make sure that the implementation in HDL is doing all that it can, and see where there's differences. This is so yeah, right on the money. And it's an iterative process. There, it's difficult work. You're mucking around with math that is not easy, and the population of people that are really good at digital, digital signal processing for the control loops of this particular type. It's a pretty, it's a elite core of people, I would say. Not everybody knows how to do this sort of stuff, and so we'll spread the word to get the word out. You'd like more eyes on it, and some some mentoring and some backup. But yeah, just keep doing what you're doing, keep hitting it, and it'll fall.
Thanks.
Yeah, sure. Very good work. All right. Any other comments or questions or input for our meeting?